Hello everybody, in this video we are going to continue with our kinematic equations and add in freefall. In a previous video, kinematic equations were used to calculate and predict the motion of objects if enough information was known, specifically in the x direction. Those same kinematic equations can also be used in the y direction. It is in this dimension that we have to consider freefall. What is freefall, or when is an object considered free falling? An object is in free fall when the only force acting on it is gravity. With that being said, if there's air resistance, then it is not considered free fall. How does gravity treat objects in the y direction? Well, it causes objects to fall faster and faster. In other words, gravity is the acceleration in the y direction. The acceleration due to gravity is 9.81 meters per second squared. Since gravity is in the downward direction, a negative sign is attached. In the y direction, there are a couple extra details to look out for. One of the things we have to look out for is whether the object's path is symmetric or asymmetric. If the path is symmetric, there are a few things that can be said about the object's motion. First, the starting velocity at the beginning of the path is equal and opposite to the final velocity at the end of the path because it starts and ends at the same height. Second, the time the object takes to reach the maximum height is equal to the time it takes to fall from the maximum height. Lastly, at the maximum height, the object has to stop before falling back down. Therefore, the velocity of the object at the top of its path is equal to 0. In this video game footage, Knuckles is jumping off from a higher edge and landing on the ground. This is considered an asymmetric path because Knuckles starts and ends at different heights. Because the path is asymmetric, we cannot say the initial velocity at the edge equals to the final velocity right before it hits the ground. In addition, if it's asymmetric, the time the object spends rising is not equal to the time it spends falling. However, the object's velocity at the top of its path is still 0. Our kinematics get slightly adjusted. The first kinematic was originally delta x equals 1/2 times initial velocity plus final velocity times the change in time. The only change there is instead of delta x, it is going to be delta y. For the second kinematic, it was final velocity equals initial velocity plus acceleration times the change in time. And the small change there is it's now written as final velocity equals initial velocity minus gravity times the change in time. For the third kinematic, it was delta x equals initial velocity by the change in time plus 1/2 times acceleration times the change in time squared. This gets modified to delta y equals initial velocity by change in time minus 1/2 times gravity times delta t squared. In the last kinematic, the final velocity squared equals initial velocity squared plus 2 times acceleration times delta x. For free fall, this gets changed to final velocity squared equals initial velocity squared minus 2 times gravity times delta y. Let's move on to an example. A toy cannon shoots a ball vertically upwards at an initial velocity of 3.9 meters per second. How high will it reach? Based off the problem, the only explicit detail given is the initial velocity, and we're trying to find the maximum height, or delta y. Since the ball is moving vertically, gravity is present. Therefore, acceleration is negative 9.8 meters per second squared. If the ball reaches maximum height, the ball has to stop, which means the final velocity is 0. Based off the known information, the fourth kinematic would be helpful to us. Let's put in the known information. We can multiply a few values and get 0 equals 15.21, minus 19.6 delta y. The rest is algebra, and we get a maximum height of positive 0.77 meters, or 0.77 meters up. This concludes our video on freefall and kinematics. Hope you found it helpful.